Good afternoon, ladies and gentlemen, President Wang. It's really a great pleasure for me, Qingyan Chen, Director of PAIR, to introduce our speaker this afternoon. Professor Pedro Alvarez is a George R. Brown Professor of Civil and Environmental Engineering at Rice University, USA. So he is a global leader in enhancing water resource sustainability through water pollution control. He is best known for his pioneering research in two fields. One in bioremediation and environmental nanotechnology. This is the second one. His research covers the environmental implications and applications of nanotechnology, bioremediation, fate and transport of toxic chemicals, water footprint of biofuels, water treatment and reuse, and antibiotic resistant control, which are very important for our daily life. So Professor Alvarez's research is highly interdisciplinary, integrating expertise in environmental biotechnology, microbiology, and nanotechnology, and using diverse methods combining contaminant hydrogeology, biogeochemistry, photochemistry, and more. So at Rice, he leads the Water Institute, called the Water Technology Entrepreneurship and Research Institute, which pursues innovation and then entrepreneurship activities in domains spanning public health, energy transition, and resilient infrastructure. He also leads the NEWT, the Center for Nanosystems Engineering Research Center for Nanotechnology Enabled Water Treatment, sponsored by the U.S. National Science Foundation. This is a very difficult center because when I was in the U.S., I tried 2 times. It consumed me more or less 99% of energy, and then I just finally give up. It's too tough. Every 2 years, there are only 4 centers being awarded in all the engineering field. You can imagine how tough it is. So congratulations for your great achievement. And of course, Professor Alvarez is a member of the National Academy of Engineering. During lunch, I learned that he's the only member in Central America. It's highly difficult to achieve this type of standard. And also American Academy of Arts and Science, and also an international member of the Chinese Academy of Engineering. So he has been awarded with the Clark Prize in 2012, one of the most prestigious water awards in the world. He also served as important roles for professional and government bodies, including US NSF Directorate for Engineering and the US EPA, and currently executive editor of the journal Environmental Science and Technology. It's also a journal I dream to publish. So I think he has really achieved the peak in whatever measures he wanted to use. And today he really just came here from Houston to Purdue to give this lecture. So that's a very long trip. He will probably stay much longer time in airplane than inland. So without further ado, please join me in welcoming Professor Pedro Alvarez.
Thank you, Professor Chen, for that wonderful introduction. I am very happy and very honored to be here and have a chance to see so many old friends and learn from you in this wonderful university. As the title implies, I'm going to talk to you about clean water and present to you a vision and some examples of how nanotechnology can help us achieve water security. And in doing so, I will be presenting primarily research that I conducted at NEWT Center, which, as you know, is headquartered at Rice, but it also comes with excellent researchers from ASU, UTEP, and Yale. I do have to apologize that I'm going to probably sit down most of the time because I am a little bit jet lagged. So with your permission, I'm going to proceed here to begin by recognizing that although we live in a water-abundant planet, the actual amount that is readily, 71% of the surface is covered by water, right? But that amount which is readily available for human consumption or to grow food is relatively small. I'm talking roughly about 0.014%. And of course, that water is subject to significant competition for different uses by different users, which reminds me of what Mark Twain used to say, that whiskey is for drinking and water is for fighting over. But unfortunately, providing clean water in an affordable and reliable fashion is getting harder because the demand for it is growing with an increase in population and changes in lifestyle, and because water pollution is becoming more complex and more difficult to treat. And on top of that, we have climate change with more frequent droughts, extreme events, and even saline intrusion in coastal areas that are exacerbating freshwater scarcity. And I also want to point out that clean water can save more lives than doctors. What I'm showing you here is how water disinfection and improved sanitation improved the life expectancy of Americans at birth from 47 years old in the year 1900 to roughly 78 years old today. This is what I call working on the correct side of the decimal point. But unfortunately, we still have 43 million Americans that do not have access to municipal safe water, and the bottom billion of our planet also lacks access to safe drinking water. Also, our water infrastructure is failing to reliably protect public health and support economic development. For example, we use way too many chemicals to treat water that generate waste streams. And in the case of disinfection, you well know that generates carcinogenic byproducts. Our Victorian era water systems, including the aging distribution systems, are leaky, which increases energy requirements to distribute water. And often they serve as breeding grounds for opportunistic pathogens that form biofilms. And then we have contaminants of emerging concerns like endocrine disruptors that affect our fertility and PFAS that we're going to talk about later. These things are breaking through conventional treatment systems. And we also face insufficient resilience of water supply. We have a water main in the US breaking every 2 minutes, losing 7 billion gallons of water every day. That's roughly 16% of the total water supply. This one broke in LA. And then a lot of times it's the power that fails to deliver clean water. In Texas, despite being an energy state, we had a power outage that left 15 million people without access to safe tap water. They had to issue boiling water notices, right? So on that note, energy for water treatment and distribution is a major sustainability issue. A typical city spends 20 to 25% of its electricity basically moving treated water. And what that suggests is that if you were able to tap local, even unconventional low-quality sources that match the consumer location to where the water is, you would basically minimize these energy and water losses through these leaky systems and decrease the energy requirements of water supply. And we also have desalination, very important in Hong Kong and everywhere. It's very energy intensity. For seawater desalination by reverse osmosis, 55% of the cost is power, electricity. So that underscores, again, the need for technological innovation to decrease energy requirements, not just to desalinate, but to treat and distribute water, right? So our vision is to enable access to adequately treated water pretty much anywhere by developing this next generation of water treatment processes that will be empowered by nanotechnology so that they're relatively small and easy to deploy, and so that they have superior treatment capacity to tap unconventional water sources and reuse challenging industrial wastewater. So our aspiration is to create clean water on demand. And of course, that may require the reuse of industrial waters or tapping unconventional low-quality sources. And we want to do that using less energy and less chemicals than conventional systems. So we are actually leading a paradigm shift to what we call fit-for-purpose distributed treatment. And there are many drivers to motivate this change. The first one is that we have no choice. There are just way too many people and industries that don't have access to municipal water because they live in rural areas or in expanding mega cities. And as I mentioned earlier, we want to save energy by tapping local, even unconventional sources. And but most importantly is that distributed treatment gives you the flexibility to match the treated water quality to the intended use. That's what we call fit-for-purpose treatment. And that's a way to avoid wasting your treatment capacity on things that do not matter and focus on what matters, right? And that decreases your treatment costs. And that's a great opportunity for nanotechnology and advanced materials to, number one, enhance the precision with which we remove the pollutants of greatest concern with higher efficiency and with I would say, higher selectivity. And the second is the ability to introduce multifunctionality so that we can remove simultaneously different classes of pollutants. And that is conducive to making treatment trains, modular treatment trains, that are smaller and easier to deploy, they're more robust, and they don't need as much energy or chemicals as our conventional system. I want to make a simple economic argument for this choice of distributed fit-for-purpose treatment. As you can imagine, the cost of treating water decreases with your size of the treatment plant due to the economy of scale, but the cost of delivering that water increases with your system size, and we end up compromising, finding a system-specific minimum that minimizes the levelized cost of water. By levelized cost, I mean a life cycle cost that aggregates CapEx and OpEx into a unit cost figure. For example, per liter of water delivered to your tap. And our argument is that if we were able to decrease the cost of water treatment at a small scale, maybe it is at the scale of a building or a neighborhood, maybe at the household scale, by introducing fit-for-purpose treatment and multifunctionality as nanotechnology now allows us, that would decrease the levelized cost of water. So that is our technology opportunity zone. That's what we're doing, okay? And so you may want to ask, well, why are we using nanotechnology then for achieving this goal? And the reason is because many nanomaterials exhibit extraordinary size-dependent properties that basically are very useful for water treatment. For example, on a per atom basis, nanomaterials are much more reactive than their bulk counterparts, allowing them to be ideal for advanced oxidation or advanced reduction processes. You take gold, for example, it's an inert material. We use it for jewelry, but at the nanoscale, it's a hypercatalyst. And carbon, which is a good insulator, becomes a superconductor at the nanoscale. Another reason is the high surface area per volume that allows you to develop high-capacity adsorbents. And if you manipulate their surface chemistry, you can make them also selective, not just to remove pollutants, but maybe to separate, I don't know, rare metals or value, other value chemicals, right? And I prefer the quantum effects, that dual behavior between particle and wave that allows you to exploit the full electromagnetic spectrum for water treatment. I'm going to give you 3 examples, mainly from my lab, not because that's the most important thing we did, but that's what I'm most familiar with. So in the first example, we're going to talk about photocatalytic treatment, which is getting a lot of attention in academia. We have had decades of papers showing how great this is. But to be honest with you, I don't know of any city that is using photocatalytic treatment at the full scale, and that's because it's very expensive. And much of the expense is because of the energy inefficiency. Of all the energy that you use to power those lamps, only about 1% ends up generating the reactive species that you need, like hydroxyl radicals. And of the radicals that are generated, only 5% or less end up being useful and reaching the target pollutant. Most of them are scavenged by carbonates, natural organic matter, and other things that don't matter. So, by the way, these statistics are summarized in this feature article where Jay Hong King, my friend, played a joke on me by drawing me as a mean boss in the red shirt. I'm not really that mean. But what I want to say is that I'm going to tell you how we address this inefficient utilization of ROS by advancing a concept that we call trap and sap. I'm going to show you how we manipulated titanium dioxide, which is a common photocatalyst that is very cheap, is earth abundant, and is generally regarded as safe. In fact, it's even used as a food colorant. A lot of times when you eat in the US those white donuts, that white stuff is not just sugar. Some of it is also titanium dioxide. And let me remind you how it works. It's a semiconductor photocatalyst that when it gets irradiated by UV, it excites an electron to the conduction band, leaving behind an electron hole that oxidizes water. And that's what generates the hydroxyl radicals that tend to accumulate near the hydrophilic surface of the catalyst. But a lot of the pollutants that we target are at least moderately hydrophobic. In this example, I'm going to use the endocrine disruptor bisphenol A that has little affinity for the surface. So the hydroxyl radicals need to diffuse away where they get diluted and scavenge, and their effective concentration decreases, and so does the rate. We want to bring the pollutants to where the hydroxyl radicals are more abundant. We want to attract them to the war zone, if you wish. And that would increase both the pollutant concentration and the reactants concentration to improve the efficiency of removal. And to do so, we advance this trap and sap, which refers to proximal adsorption to reactive sites. So we used a very common polymer that is earth abundant and cheap and safe called cyclodextrin that has a property, looks like a bucket, that has a hydrophobic cavity where the pollutant can fit, and the rest is, of course, hydrophilic. And using a simple refluxing method, we partially coated titanium dioxide to enhance with the trapping function. In this case, we actually made titanium dioxide nanosheets to maintain high surface area, but we assembled them into micron-sized hierarchical spheres. We wanted them to be larger so that could be easily separated and reused by, for example, low pressure filtration. And as you can see here, they look like flowers, except that they're more like a Venus flytrap. The fly in this case is the green dot, which is the bisphenol A. This enables proximal adsorption next to where the hydroxyl radicals are generated so that you don't waste them or don't get them scavenged. And you can see here the benefits by looking at the blue line, which shows you that the rate of degradation increased by 5-fold. Of course, if the rate increases, that means your contact time under UV radiation can be shorter, so you use less energy. In fact, the electrical energy per order of reaction decreased by 5-fold, which is encouraging. The problem is that cyclodextrin is organic, so it deteriorates with the hydroxyl radicals attacking. You start noticing deterioration after 500 hours of intense UVC radiation. So we cross-linked the cyclodextrin with a fluorinated polymer. No fluoride or PFAS or anything like that was released. We checked for that. And serendipitously, that not only increased the absorption capacity, but also the absorption rate. And as you can see here, the durability after many cycles enhanced. So that was the good news. And we also used this trap and sap approach to enhance disinfection of wastewater treatment plant effluents to destroy not just bacteria, but antibiotic resistance genes that they may release. I found a while ago, looking at some Tianjin wastewater treatment plants, that they can be breeding ground for superbugs, multi-drug resistant bacteria. And when you kill them, they release these resistance genes that get stabilized in the sediments of the Higher River. They get stabilized by clay. And in the sediments, they transform indigenous bacteria that increase the environmental resistance. So it's very important to not only kill the bacteria, but also destroy these bad genes. And here we use a different catalyst, bismuth oxide, and we coated it with reduced graphene oxide, which has high affinity for the bacteria, but also for the genes that are released in the immediate vicinity of the catalytic site, again, to mitigate the dissemination of antibiotic resistance from wastewater treatment plants. In the second example, we're going to talk about per and polyfluorinated substances, which, as you know, are ubiquitous emerging pollutants that are very, very resistant. Thank you very much. They're so resistant that they earned the nickname of forever chemicals, and they're showing up even in the blood of newborn babies nowadays, right? If you drink it, it takes you 7 hours, 8 years to excrete it, right? You may remember that these compounds were developed as part of the Manhattan Project to enrich uranium in the 1940s. And their use grew and diversified, and that resulted in widespread environmental pollution, which is of great concern because it creates a lot of chronic effects ranging from cancer to developmental toxicity. So the EPA, not surprisingly, passed the most stringent water quality standard ever for any pollutants for a couple of these PFAS, like PFOA, for example, which is the most common. This standard of 4 parts per trillion is about 4 drops in 1,000 swimming Olympic pools. It's about trying to find 1 person in 30 planet Earths. It's that hard, that stringent, the standard, right? And there was a recent analysis by Global Water Intelligence that shows that the most commonly used techniques right now to remove PFAS from drinking water are based on separation. I'm talking about mainly activated carbon adsorption or ion exchange or reverse osmosis filtration. But we favor degradation technologies over just separation that just transfer the problem from one phase to another, but they do not eliminate toxicity or potential liability in the future. And there are many, as you can see in the bottom left, degradation processes that are being developed, but they are at relatively early stages of development, and they face significant scalability challenges, and they would greatly benefit from fundamental research to understand their mechanism and their merits and their limitations. Now, many of these processes are advanced oxidation processes that rely on radicals like hydroxyl radical or superoxide. So we decided to investigate how important are these radicals, which radicals work, which ones don't. To my surprise, we found that neither hydroxyl radicals nor superoxide can initiate the attack of PFOA, even under exaggerated conditions where you use insanely large concentration of hydroxyl radicals, for example, in photophantom reactions. So I want to caveat, although they don't participate in the initial attack, they can help with the fluorination by attacking byproducts. But my point is that it is very difficult to publish negative results, as you can imagine. I don't know if you ever tried to publish a negative result, but we did, because it resolved a controversy about the PFOA degradation mechanisms. And it highlighted the need for more analytical rigor in PFAS research. For example, you need to strive to measure the released fluoride concentrations and get fluorine mass balances to demonstrate that your removal is really due to destruction and not to something else. And these papers also inform practitioners to avoid advanced oxidation processes that rely on these radicals and consider other reactive species. So along those lines, we discovered that chlorine radicals that can be formed by 2 things that are commonly found in water treatment plants, chlorine and UV, that generates chlorine radicals. They actually degrade and defluorinate PFOA, and the way they do it as many other processes do, is that they remove one electron from the carboxylic end of the PFOA, and that destabilizes the molecule, and it initiates the decarboxylation, hydroxylation, elimination, and hydrolysis pathway, the DHEH mechanism. So it actually works that way. But I want to switch to advanced materials and share with you that Mike Wong discovered serendipitously that hexagonal boron nitride can serve as a semiconductor photocatalyst that efficiently degrades and defluorinates PFOA. This is a well-known material widely used in the nanoelectronics and cosmetic industry because of its thermal and lubricating properties. It is commercially available easily, it's cheap. It's actually known as the white graphite. Mike just happened to find a new and important application for it. And molecular modeling and density function theory analysis showed us that the action occurs at the electron hole. What happens is that the electron hole is hydrophobic, and therefore water doesn't get in to compete for the oxidation capacity of the hole, and the PFOA is degraded more efficiently. And we were able to scavenge the hole by using EDTA, for example, to show that you could quench the reaction that way. And we work in our center with a lot of industries. One of them is Purifics, which loaned us this pilot scale photocatalytic reactor, and we got pretty encouraging results. As you can see here, we achieved nearly complete removal to meet the drinking water standards with 1 hour of treatment. And with 6 hours irradiation, we achieved near complete defluorination. What is interesting is that this catalyst works really well also in the presence of salt. And that is very rare. Most photocatalysts get very inhibited by salt. So that suggests that we can use it to treat brines that are concentrated from reverse osmosis or from ion exchange membranes before they are disposed of, which is an increasing need. And in this last example, I use also a trap and zap approach, but this time for an electrochemical process. I'm a big fan of electrochemistry because it gives you an opportunity for tunable treatment that is also modular. And in this case, we use again this hexagonal boron nitride, but not as a catalyst. We use it as a hydrophobic coating of the anode to keep the water out and don't steal the oxidation capacity, and also to attract the hydrophobic tail, in this case, of PFOA. And in this case, we also use a metallic organic framework, a MOF, called UI 066. It's called like that because it was invented at the University of Oslo in Norway, right? And that's a known adsorbent that helps with the trapping function. We found that it worked best at a ratio, a molar ratio of 1:1 to HPM. And as you can see here, decorating the anode with this mixture, this coating of HBN with the MOF, significantly enhanced the removal of PFOA 93% after a couple of hours. The MOF itself is not conductive, so if you just coat it with the MOF, it doesn't do anything. It just helps with the trapping function. But if you try this without any coating, nothing happens at the low voltage that we were using. So that shows you the benefit of the trap and zap approach that decreases energy requirement. We were able to achieve an electrical energy per order of reaction, an EO value of 6 kilowatts per cubic meter, which makes it very competitive. So to ground what I just told you, the trap and zap strategy aims to separate target pollutants from complex mixtures, remove them away from interfering compounds, and concentrate them near reactive sites for more energy-efficient destruction. And we can apply this through many strategies. We can include physical barriers for site exclusion of large interfering compounds like natural organic matter. We can manipulate the catalyst surface to enhance its affinity, maybe electrostatically attract the carboxylic head groups or hydrophobic interactions with the tail. We can even try molecular imprinting of polymers. We never tried that for PFAS, but we did it for sensors for COVID. where we were able to selectively trap with a molecularly imprinted polymer the spikes of the polymer of the COVID-19 virus. So anyways, it's encouraging, but we're just beginning to try these things. In my final example, I'm going to talk about the eradication of biofilms, which is a major problem in water distribution and storage systems because they may harbor pathogens and they may stimulate corrosion. And both of these are multi-billion-dollar challenges. And unfortunately, our current approaches that involve chemical disinfection don't work well because biofilms, you only kill the outer layer. The bacteria that are inside are protected, and all of these chemical disinfectants have limited diffusion capabilities. So we are pioneering the use of bacteriophages in various environmental applications, including biofilm control. I'm not going to have time to show you how we use them to fight superbugs in activated sludge or to displace antibiotics in animal agriculture to mitigate the spread of resistance. Phages, let me tell you, are viruses that exclusively infect bacteria, and they are by far the most abundant biological entity on Earth. It's about 10 to the 31 of them. They're also the most diverse, and I would say the most underutilized biological resource. I view them as self-replicating green biocides that are safe because they cannot infect humans or insects or plants, not even protozoa, only bacteria. The guy on the left here is Félix Derel. He was sort of French-Canadian French, and he pioneered the use of phages to treat infectious diseases. Most of this work was done at the Eliava Institute in Tbilisi in Georgia. And Western medicine has suddenly rediscovered this forgotten cure when we're dealing with more superbugs and you have a antibiotic-resistant burn victim, for example. And the FDA has approved just about every application involving phages, not only for treating human diseases, but also plant diseases. And we developed a method to isolate polyvalent phages that have a very broad host range and can attack a wide variety of bacteria. But even polyvalent phages have a hard time penetrating biofilms because of diffusion limitation. But we wanted to reach the bottom of the biofilm very quickly so that they can attack it from the root and de-anchor it. And to do so, we conjugated them using amide bonds with super paramagnetic nanoparticles that serve as, I call them magnetic Trojan horses that deliver the cargo. All you have to do is apply a weak magnetic field to push them into the biofilm. Then they release the phages, and if you reverse the magnetic field, you pull them back out, and you can reuse them. And you can see them in the far right quadrangle. You see some rows that are the bacteria that are being attacked by these super paramagnetic phage conjugates, which are the spheres. And as you can see here, I'm showing you an epifluorescence image of a biofilm in the far left, which is the initial conditions. Next is what happens when you add the particles alone without the phages. There's some physical disruption as you push them in and push them back out because they're not toxic. This is essentially rust. This magnetite, by the way, is used as a food colorant to make chocolate look darker, right? So it's safe. Next is phages only. These phages did really well because they are special phages that we isolated that they pack their own polymerase enzyme, depolymerase enzyme. But they don't do as well as when they're conjugated into these magnetic Trojan horses, as you can see. We also are exploring the use of phages to mitigate biofouling of household water storage tanks. This is very common in developing countries where you have a fiberglass tank that if you don't clean it often, it biofouls and it can cause disease. And in this case, we're using a responsive polymer coating that swells when it senses that a biofilm is forming because biofilms generate fatty acids that decrease the pH locally. And that local decrease in pH is enough to swell the polymers and autonomously release the phages on an as-needed basis. The polymer that we use is very difficult to pronounce. It's a nano-encapsulated chitosan with tripolyphosphate and glycidoxypropyl trimethoxysilane. You need to try that at home. And I want to point out that when you artificially decrease the pH of the water to, say, 5, that immediately releases the phages that are viable. Even if I leave these capsules with the phages inside for 1 month in tap water, they're still viable after 1 month. In fact, a long time ago, I was thinking of applications for third world countries and figure out a way to store phages without refrigeration. So we encapsulated them into the spores of Bacillus subtilis, which you can trigger germination easily by adding them a mixture of amino acids. And they stay viable for over a year. So we think that this can stay viable for a while. And if you look at this confocal microscopy image with a SNAR4 dye that detects local areas with low pH, those red dots are areas where the local pH decreased sufficiently to trigger polymer swelling and phage release. So does it work? Yes, it does. Take a look here. First of all, you can actually coat the floor, the bottom of the storage tank that is prone to biofouling using plasma-treated surfaces. And you can see that the uncoated surface gets foul. If you coat it only with the nanocapsules without any cargo inside, without phages, it fouls. But if it has phages inside, they do not foul. And this has a big advantage over the previous approach in that this is a bottoms-up attack. You attack the biofilm as it begins to form from the bottom of it, as opposed to top-down, which suffers from diffusion limitations. And this confocal image shows you a visual representation of the benefits of this coating of plastic surfaces in terms of mitigating the, of course, biofouling. Before I wrap up, I want to make a comment about innovation, which I view as climbing a mountain, but having to cross 3 valleys of death. The very first valley of death is the valley of the idea. This is where universities conduct use-inspired basic research, and we de-risk these ideas. And then we move to the area of accelerating translation to practice, which is often in the domain of accelerators and incubators, where our startups get nourished by, or they get bought by venture capital, or they grow with industrial support. And here, it is very important to collaborate early on with our stakeholders, industrial stakeholders, that pull what we push. Because if you're just pushing without anybody pulling, it's doomed to fail. When you're looking for problems for your solution, that it doesn't work that way. And then the third valley, which is the valley of the scale, that's for those big ticket breakthroughs that are demonstrated to be techno-economically feasible in the middle bridge. And that's really 1 out of 10, roughly, that essentially with some large scale investment by corporations or by government, they actually make it. But my point is that we build bridges mainly in the first valley, and we also try to get more people to reach the top of the mountain. And we do that by encouraging students to attempt the climb and to empowering them by entrepreneurial training, like teaching them how to, yeah, I only need 1 minute. To do entrepreneurship, how to write a business plan, and how to do techno-economic analysis. That's part of the things that we do in our center. So based on these principles, NEWT became a very effective innovation ecosystem to find solutions to complex water quality challenges. And together with our 20+ industrial members, many are Fortune 500 companies, and up to 30 faculty labs across 4 universities, we built collaborative test beds to de-risk technologies and accelerate innovation. And we have existed over 9.5 years. And we have been very productive in the sense that we published more than 900 research journal articles. We generated a lot of IP and startups, and we train a globally competitive workforce, including 42 newly minted faculty members. And of course, we welcome collaboration, which is why I'm showing you this slide. So to conclude, my take-home message is that nanotechnology offers the potential for beneficial, disruptive innovation for both drinking water treatment and industrial wastewater reuse. We can develop advanced materials and enabling technologies such as this that I'm listed here that could be integrated into compact and high-performance modular systems. Now, Steve Jobs used to say that people don't know what they want until you show it to them. And you know, about he showed us smartphones 15 years ago. I didn't know I needed one, and now it's hard to function without one. And in a similar manner, the high-performance modular treatment system that we are trying to deploy and beginning to deploy are going to be like the smartphones of the water industry, in the sense that they're going to allow us to give a multifunctional service even in areas with limited infrastructure. So with that, I would like to thank the National Science Foundation for funding the Newt Center. I want to thank especially the students and colleagues that generated much of the data that I presented to you today. And of course, I want to thank you for this invitation and for your attention. Thank you so much.
Good afternoon, and this is Tao Wang from Civil and Environmental Engineering, and it's my pleasure to chair the session. So maybe first we should give another round of applause for the excellent presentations by Professor Alvarez. Thank you very much for this interesting talk.
Thank you, Professor.
So now it's time for Q&A from the audience, and any questions from you, and it's a time opportunity for you. Further, John.
Thank you, Professor Wang. Thank you, Professor Alvarez, for your great talk. Very insightful, very informative. So I like your ideas of absorb some pollutants and then to fully improve the utilization of radicals in photocatalysis with nanomaterials. And also I like your idea of to use nano-conjugated phages to effectively remove biofilms. So I have a special question. So for perfluorinated compound removal, so I look at your slide. I found your y-axis is the PFOE remaining concentration. So is that the removal of fluorine from PFOE, or it's mainly a decarboxylation to remove a carboxyl group from PFOE? So this is a special question. So a general question is that, so for nanomaterials in water treatment, so after the treatment, so do we need to remove those nanomaterials, or in most cases, it's okay so for them to stay in water?
Yeah, no, it is an excellent question. When we began working in nanotechnology, we asked the question, is this going to be a new class of environmental pollutants that we need to understand better? How do we ensure that nanotechnology evolves as a tool for sustainability rather than an environmental liability? So we did a lot of proactive risk assessment and decided to always use nanomaterials that were inherently safe, made of elements that were harmless, and that we immobilize them as much as possible to eliminate exposure. And of course, by immobilizing them, we would amortize their cost because we would be able to reuse them. We just published a review about all of this evolution of nanotechnology and the safety concerns in the a journal called Nature Ecology and the Environment, one of the baby nature journals that it sort of goes through the whole history of this. But the bottom line is that we also consider public perception and did a lot of surveys. And we work with NSF International that certifies products used for many different things, including for water treatment. And of course, before we advance to the second value of death, we kick the tires in our lab, make sure they don't come out. We do ecotoxicological studies and basically make sure that this is relatively safe. Nothing is 0% safe, but a lot of times it involves trade-offs. And the alternative is the pollutants in the water that if you don't remove them, they for sure are going to harm you much worse. So, but thank you for your question related to the safety and perception about nanotechnology.
Thank you.
Yes, please.
Thank Professor Pedro for the nice talk. I'm just curious about because you mentioned the boron nitride can do the photocatalytic degradation. But in my understanding, normally the band gap is a little bit higher to do photocatalysis. So this one kind of modification or something like that to tune the band gap so that it can degrade the pollutant.
Yeah, you don't need to do any band gap engineering. We recently did. We doped it with iron to enhance attraction to the carboxylic side, and we found that doubled the extent of defluorination. Just published it in one of those ACS journals about advanced material. But it actually, the data that I show you with full defluorination, it's commercial as you buy it without doing anything to it. So I don't know if it's, certainly you can do band gap engineering on a lot of things, but I'm not sure if the benefit to cost ratio justifies it always, right? But it is a good point to think about this, absolutely. I mean, and as you know, doping can help in some situations. In this case, the hole's oxidation capacity was enough to remove that single electron that allow you to destabilize the molecule.
Okay,
Yeah.
okay. Thank you. I have another question because you mentioned that can use the photocatalysis combined with chloride to degrade the PFOA, right?
It was not photocatalysis, it was more like photolysis, but yeah, I mean, it was UV. If you irradiate chlorine gas with UV, you can generate chlorine radicals.
Okay, so this is kind of a new method to.
Yeah, but I was just showing you in the sense, I'm not advertising this as a practical solution, right? I'm just showing that you could generate chlorine radicals that react and defluorinate. But I haven't done any techno-economic or feasibility analysis to see if it makes sense. I worry, to be honest with you, that chlorine radicals can also react with other things and chlorinate things, and who knows, maybe have unintended impact, like generate carcinogens or other toxic byproducts. That's why I'm not advocating that. I presented that more to illustrate the realm of reaction possibilities that could occur in a water treatment plant.
Okay, okay. Thank you very much.
Yeah, yeah.
Utah?
Thank you, Professor Alvarez, for the very inspiring talk. So my first question is, I noticed from your presentation, most of the concerns actually are emerging concerns like the ARG, ARB, or the PFOA, right? So my first question is, for this nanotechnology, do you think there are some niche which we could apply to the traditional contaminants in water or wastewater, like nitrogen, phosphorus, or organic carbon? That's the first question. The second question is, myself actually is more focusing on the biotechnology for water treatment. So that's why my second question is, I'm just curious about your insights for the comparison between biotechnology and nanotechnology. Which one do you think would be the future for the wastewater treatment? Thank you.
No, excellent questions. Related to the first question, can you use nanotechnology to treat conventional pollutants? And the answer is yes. For example, nitrate, we can make nanocatalysts that reduce nitrate to nitrogen gas, which is unprecedented. Most reductants reduce it to ammonia, which interferes with chlorination, or you haven't really removed eutrophication potential and so on. And this way you can take it to N2 if you don't want to recover it. I only would recommend that you consider nanotechnology when it can do something that you cannot do by other ways, and when it can decrease the total cost or improve rates. Related to biotechnology, I like combining them because bacteria can do a lot of the heavy weight lifting. For example, for PFAS, right? If you use nanotechnology to just transform the molecule into something more biodegradable, and then follow that up with a biological treatment process to complete the defluorination, because many bacteria, there's 15,000 different PFAS. Many of them are biodegradable. If you could transform catalytically a tough one into something more biodegradable, that integrated sequential treatment might actually be cheaper. I'm always a big fan of nature-based solutions. I mean, my roots are in biological treatment, so.
Hi, Pedro. It was a great talk. Third time attend your talk. So, but more questions. First question I have is regarding, your center has quite a few startup companies. And then when you're showing the chart from the Global Water Intelligence showing that active carbon is on the right, I think every startup company that deal with water treatment probably need to kind of compete with active carbon, because it's just cheap and effective for so many things. What's your experience like, or people over there like in kind of addressing, how to compete with ion exchange and active carbon technology?
So at least in the US and in many other places, water treatment is driven by regulations. And what people do is they try to meet the regulation at the lowest possible cost. And they're not necessarily being eco-responsible and worrying about byproducts that are not regulated and so on. In the case of PFAS by activated carbon, there was a ban temporarily, because when you regenerate the activated carbon and try to destroy it in an incinerator, they realized that they were emitting a lot of volatile emissions, and they were worried about that. So that gave rise to these alternative companies that are based on electrochemical or other processes. But municipalities, in my experience, are very conservative, and they don't want to consider a new treatment process unless you guarantee them that you can save them at least 20%. If it's only 10%, too risky. They don't want to change. The part of the inertia is the existing infrastructure, the inertia to innovation, right? But in the case of PFAS, there is room in the realm of distributed treatment. And for example, for the Taiwanese semiconductor manufacturing company that just opened a big factory in Arizona, they need to treat PFAS, the semiconductor industry, for example. In our institute, we launched a center of excellence for PFAS abatement and replacement. We're also trying to find replacement chemicals. And I think that that's the long-term thing that we need to focus on, not just destruction.
Yeah, so on the related question regarding PFAS, right? So a few days ago, read an article on New York Times about farms in North Carolina or maybe other place in the US. Acres of lands are heavily polluted by PFAS, right? So right now, I think people care about like the end point treatment. Before you drink it, you make sure it's PFAS free. But the reality is, every time rains, those places, kind of rinse off a lot of PFAS and go into the water stream again. I just kind of wonder if, how can we address the issue holistically rather than just focusing on the very end? Any insight on that?
Yeah, no, you're right. I mean, a lot of times ends up in the sludge and the biosolids that get applied to agricultural fields. Obviously, prevention is a lot more important than remediation, right? But I will tell you one thing. People are re-evaluating the data that was used toxicologically to classify PFOA and those at that level of carcinogenicity. And if they succeed through the scientific debate, they may relax the stringent standards. I'll just say that for now. Sometimes, we worry about things in water that can kill you in 2 or 3 days, and sometimes you worry about things that can kill you in 30 years, right? Which are the emerging pollutants that you were referring to.
Thank you.
Yeah.
Thank you, bro. I have one question about the PFOA. The conventional system, like we know about the thermal way of treating water, like MED or MSF. Can we remove PFOA using these technologies? I mean, these old conventional technologies. Can we do that? Because recently we have another technology is known as interfacial solar steam generation. And I think there are some research for 10 years still going on. So this system is actually using solar thermal energy to produce steam and then condense it to make pure water. So can we use this technology to remove PFOA? I mean, what is your thought about it?
Yeah, I think so. I think there are many conventional technologies like activated sludge. You can remove it, but not enough to meet the quality standards. That's the problem, right? I mean, that's why it ends up in biosolids, because you're removing it, but a lot of it still comes out. I think that many technologies that appear to be extremely expensive could become feasible if you can separate the PFOA and concentrate them. If you have to spend a lot of energy, but on a very small volume, then it might become feasible for destruction purposes than if you have to do it on a dilute solution, right? So, but yeah, absolutely, I agree with your perspective. Thank you.
Any other questions? And actually, there is one from a registrant, and his question is, I think it's about application of reduced graphene oxide in water treatment. I think that seems his question. Maybe do you have any insight?
Yeah, I don't think it's going to be very feasible or widespread. We wanted to illustrate with that the trap and zap approach, which refers to proximal absorption and concentration of a target pollutant near a reactive site, could be applied in different platforms. And I show you that we could do it in the photocatalysis for both bacteria and chemicals. I show you we could do it in electrochemical systems and many other types of systems, including advanced reduction systems. But I don't seem to imply that we never did a techno-economic analysis. A lot of times we do research at relatively low technology readiness levels from 0 to 2 is where I typically work on.
Okay, thank you. Any other questions? Maybe I have one.
Yes.
So I'm not in this field, but it's very interesting to learn, all these different nanotechnologies used in the water treatment.
Yeah.
I wonder what's the current applications in like industrial scale or in the immediate future of these, new.
Yeah. So we have worked with Amway, for example, who makes activated carbon filters, and by I'm going to use the word nanotizing them, Paul Westerhoff added titanium dioxide as an absorbent for arsenic because those filters couldn't basically remove arsenic, and now they can. That's an example. Qilin Li developed a process to desalinate water using sunlight. We know how to desalinate, but as I show you, over half of the cost is electricity. But she uses a free source of electricity, the sun. This is a nanophotonic enhanced membrane distillation. The idea is that when you shine light into these nanoparticles, you excite the outer shell of electrons that begin to oscillate, creating a surface plasmon. And that's a highly local photothermal effect that causes water to boil. And the vapor trespasses a hydrophobic membrane and becomes distilled water on the other side. So obviously, this is not something for areas where you need a very large surface area, but she's using it for various applications. She has a startup, so that's another thing that is moving along. So, you know, those are just two examples. Yeah.
Yeah, this is very important, of course. Yeah.
Yep.
Okay, please.
Okay, thank you, Prof. Pedro, for your nice talk. And I have two general questions. The first one is we have developed many nanotechnologies or materials for the removal of micropollutants in the wastewater. However, this micropollutants have very low concentration. Even we need to much more effort to remove it in the wastewater. So how to balance the cost and the low concentration micropollutants in our traditional wastewater treatment system? This is the first question.
If I understood you correct, you're sort of saying that the micropollutants are present in a complex mixture, and how are you going to effectively treat them with nanotechnology? Is that the question, or?
How to balance the cost and the
okay.
low concentration.
All right, let me tell you three things about the cost of nanomaterials. Most of the cost is not making the nanomaterials, but purifying them. To publish, you need a highly pure nanomaterial so that you can truly understand the properties and so on. But I can make a 99% pure nanomaterial as long as that 1% impurity is not harmful, and that can cost me 1,000 times less, because most of the cost is associated with separation and purification of the nanomaterial. So number one thing you need to do is avoid the diminishing returns of ultra-high purity. Number one. The second thing is you immobilize them in a manner that they don't lose their functionality to allow you to recycle them and reuse them. And if you reuse them over and over, that amortizes their cost. And the third thing is you don't need much to make a difference. Only a little bit in catalytic quantities can make a big difference in terms of the removal of recalcitrant micropollutants. So that's my answer.
Okay, the second question is, in the past few years, people focus on the pollutants removal or degradation in the wastewater. But now many researchers consider the resource recovery or the carbon capture is also the direction for the future wastewater treatment. So what do you think the opportunity for the resource recovery, or I saw the one direction is the lithium extraction in the wastewater or the brine. So how do you think the opportunity for the resource recovery or the carbon capture in the wastewater treatment?
It's certainly worth considering. In general, recovering nutrients like nitrogen and phosphorus from wastewater, to be honest with you, doesn't pay, because it costs you more than the value and the alternative. You always need to benchmark whatever you're doing to other performance metrics or other alternatives. But if you have, for example, produced waters from the oil and gas industry, the fracking waters, they have lithium. And you might be able to selectively separate them and recover them. And in that case, the value of what you recover might exceed that. And if I have a mining industry, maybe I might be able to recover rare earth metals. And the nanomaterials allow you to be very selective about separating them, and hopefully you get more out of it than it costs to do so. But yeah, you gotta consider the cost. It's possible to do it, but not always advisable.
Okay, thank you.
Okay, so do I have any questions for Professor Alvarez? And if not, let's thank Professor Alvarez again for the insightful discussions. Thank you.
Thank you.
Thank you. Thank you. Nice to meet you.
To express our appreciation to Professor Alvarez's excellent presentation. So please make this flag as a token of appreciation. I also like to take the opportunity to thank all of you for attending this distinguished lecture today, and especially for those who ask questions, which make the presentation even more useful. And please remember that PAIR organizes this distinguished lecture from time to time. This month, on the 20th of May, we have another lecture will be given by Professor Marcus Liu, who is the Vice Chancellor and President of the Surrey University in the University of Surrey in the UK, who is also coming in the transition to be the President and Vice Chancellor of the University of Wollongong in Australia from this month. So his research is related to chemical engineering and nanotechnology. So I welcome all of you because this lecture will be very similar, I mean, in more or less the same domain like Professor Alvarez. Okay, thank you very much. And this lecture is adjourned.